Hello people, welcome to Gurukula. I'm Jai. So today in this video we will be talking about link state routing. So without any further delay, let's get started. In our previous video, we have spoke a lot about the distance vector algorithm, and with this note, let us see what is link state routing. And in this video, we will be covering the introduction to link state routing, and then we will see how the link state routing actually builds the routing table, which actually takes 4 steps in total. The first one is creation of link state packets and flooding of link state packets, formation of shortest path tree, and calculation of routing table from the shortest path tree which is created in the previous step. So these are all the various things that we will be discussing in this particular video, and certainly we will also be talking about the protocol called OSPF protocol in the next upcoming video. So just to recap the types of routing protocol, these are all the types of routing protocols that we have. We have already discussed one type of interior gateway protocol, which is distance vector routing, in the previous video. In case if you have not seen the previous video, I will just leave the link in the I button and as well as in the description section. So please do check out the previous video for the better understanding. And in this video, we will be talking a lot about link state routing, and in the next video, we will be talking about the OSPF protocol. And to keep in mind, and the link state routing protocol is an interior gateway protocol. So just to introduce you to the link state routing, it is the second major class of intra-domain routing mechanism, which means that it is used to help to route the packets within an autonomous system. So you cannot able to route the packets between autonomous systems by using link state routing, because this is an interior gateway protocol, so that you can route the packets only within an autonomous system. The ultimate aim of the link state routing protocol is to find the shortest path to any other node available in the network. So we will see how the link state routing algorithm is forming the shortest path to all other remaining nodes in a minute. So to calculate the shortest path, we need to provide certain informations to the node, and based on the informations that we provide or the node provides itself, the shortest path will be created. And the link state routing are much more complex than the distance vector routing, but this complexity comes with an much more of features. Say for an example, your distance vector routing algorithm will take longer time to converge, but whereas your link state algorithm converges at a very faster rate. So just to get the difference between the link state routing and then the distance vector routing. In distance vector routing, this is what the example network that we have discussed in the previous video. And as you could see in this particular video, each and every node will just have the information of just the next node. So let us take for an example, if E has some packet which has to be destinated to D. If E wants to send this packet to D, now let us see what will happen in this particular thing. E does not know what is the complete route that this packet will take in order to reach D. So when you look at the routing table of E just knows that D can be reachable with the cost of 9 when it goes via C. So E has only the knowledge that it has to pass on the packet to C. So E doesn't have any knowledge of where exactly the packet goes beyond C, and E does not know what actually C does with that packet to deliver the packet to D. So as of distance vector routing algorithm is concerned, each and every node will know only about the next node, not the entire network. This has to be kept in mind. Once the packet has reached C, then looking into the routing table of C, we can see that C can reach D with the cost of 5 when it goes via A. So C just knows that the packet has to be sent to A, and A will take the responsibility of delivering the packet to D. And finally, when the packet comes to A here, looking into the routing table of A, the destination is D, so it can be reached with the cost of 3 and it is a directly connected node. So A is actually delivering the packet to D over here. So when you look into the complete process, E does not know that the actual path is, this is what the actual path, from E the packet goes to C, and from C the packet goes to A, and from A the packet goes to D. This is what the complete route that is taken by the packet, but E just knows only about the next hop, and C just knows only about the next hop. And this is what we have in distance vector routing. But whereas in linked state routing, the scenario is a little bit different. So we will take the same network again over here, and then we will see how the routing tables are created, especially when we use linked state routing algorithms. So here in linked state routing algorithms, each and every node will know the complete structure of the network, and this complete structure of the network is what we call it as the topology. So each and every node in the network has the complete topology in the mind, and by using this particular topology, the node will create its own routing table. The node will create its own routing table. So as you could see in the complete figure, A also knows the complete structure, which means the topology. B knows its topology, and C also knows its topology, and D is also getting the same topology, and E is also getting the same topology. So the topology of the network is known to all the nodes present in the network, and then by using that topology, each and every node computes their own routing table in order to route the packets from the source to the destination. And even though each and every node has the same topology, the routing table will not be the same for each and every node. So that is a speciality and the key point which we need to keep in mind in the linked state routing. And the analogy to understand this particular topic can be seen as, this is like each and every person is having the city map in their hands. So in a city, they will be having the city map. The city map is going to be common for each and every one, but the route what each and every person takes will be different according to the destination part. So the topology can be equated to the city map, and then the routing table can be equated to the actual route a person that is taking in the city. So that is how the linked state routing is getting differed from the distance vector routing. So now looking into the various steps that is involved in linked state routing, we have 4 different steps to be followed. The first one is each and every node will create the linked state packet. And in the second step, the created linked state packet has to be flooded to its neighbors. And the third step that we need to do is the formation of shortest path tree. And finally, we need to compute the routing table from the shortest path tree which is created from the previous step. So now let us get deeper into each and every step. Our first step is creation of LSP. So generally the LSPs are created with huge amount of information in it. But in this video, for the sake of simplicity, we will just assume that the LSPs are created with very minimum and important amount of data. And there are few important informations that each and every LSP will have, out of which these are all the 4 important informations that each and every LSPs will have. Node identity and list of links, sequence number, and then the age. Out of these, node identity and list of links will help the other nodes in the network to create the topology. And the sequence number will facilitate the next step, which is flooding, and it also helps to differentiate the LSP packets from the new packet to the old packets. And finally, the age, this is as similar to your TTL, which is time to live, which helps to remove any old packets from remaining into the network over a period of time, because any unused packet on the network will create unnecessary congestion. And now comes the question, when should I create the LSP packet, or when the nodes should create the LSP packets? Well, the LSP packets will be created on 2 occasions. First, when there is a change in the topology of the domain. In case if there is any node that has got disconnected from the network for any reasons, or if there is any addition of nodes that is added on to the network. So in case if there is any change in the topology of the network, then LSPs has to be created by each and every node, and it has to be disseminated to all other remaining nodes in the network. So this is one occasion on which the LSPs are created by every node, and the second one is on a periodic basis. You very well know what periodic basis is. For each and every 1 hour to 2 hour, this is the normal time span when the LSPs will be created. So this is not necessary actually, but still it is a best practice to create the LSPs on periodic basis, just to ensure that each and every node is getting updated on time. So that is all about the creation of LSPs, and we will see what happens after creation of the LSP packets. So next step is flooding. Let's see what flooding is. Once the LSPs are created, it must be disseminated to all other nodes in the network. Keep in mind, it should not be disseminated only to the neighbors, because each and every node in the network should know about the complete topology of the network. So in order to do this, we need to send the LSPs to every node in the network. So how it can be done? So this can be achieved by the process called as flooding. So let us keep this particular network in our mind, and then we will see the node will be created with the LSPs, and then it will send the LSP out of each interface. Just keep in mind, the LSPs, the creating node will send the LSPs out of each interface. Let us assume in this particular figure that the A is creating is LSP. So let us assume that this is the LSP of A, right? And now what happens is, this is the creating node. Now A becomes the creating node, and A has created its LSP packet, and we very well know what will be the content available in this particular packet. So the first one is the node identity. So the first one will be node identity. So node identity is nothing but any number that is used to identify this particular node onto the network. Generally, it will be an IP address. And the second one is the list of links. The list of links is nothing but A comes to know that A will be disseminating the information about the neighbors. So A is connected to B, A is connected to C, and A is connected to D. And this is what the list of links that the A will have. Third information what we have is the sequence number, and the LSPs will be given with some particular number, say 1, 2, 3 or 4, or any sequence number, which will help us to identify the new LSP and then the old LSP. Let's take for an example, if A node creates another LSP packet after if there is any modification on the network, the sequence number will be incremented by 2. So now this sequence number will help us to identify which one is the new LSP and which one is the old LSP. So this is again the LSP created by A after some modification on the network. So this sequence number will help us to identify whether this is a new one or the old one. And finally, it will have age in its content. So this age will help us to identify how long this packet has to be there onto the network. This is as similar to time to live. So that is the very first step which we have to do. We have the creating node will create the LSP, and it sends out in each of its interface. When you look at this particular figure, A will send its LSP to B and C and as well as D. So these are all the interfaces that A will have. So now let us see what happens next. Now the receiving node compares the LSP with the copy it already have. So in case if B has already got the copy of LSP A, so let us assume that the B already have the LSP of A. Now it receives another copy from A. Now the B is the receiving node, and this particular receiving node will check the two copies of LSPs. Now if the received LSP is the older one, then B need not update anything. So simply the B will discard the packet which is being received. and in case if the node is new, in case if the LSP is the new LSP, then B will update its own table, so keeps the new LSP and then it discards the older one. And not only that, it will also flood the copy of LSP to all its interface except the one from which it came in. So this is very important to understand. This is how actually the link state algorithm floods all the packet to all the nodes in the network. So what happens here is, on the case of the LSP, that is the new one, then B will discard the previous entry and then it will keep the new entry in its table. And not only that, it will send the table to E and as well as C. So it will not send the packet to A because that is where it actually came in. So this side of transaction will not happen from B side. So that is what given over here. So the receiving node will actually flood the new copy of LSP in all the interfaces except one through which it came in. So this is how the flooding will occur. And this process will keep on happening at each and every node, and this process of exchanging LSPs will stop at one particular point when the node has only one single route to reach the destination. So that is all about the flooding, and now we will see how the shortest path tree is being formed. So the formation of shortest path tree will be done once after receiving LSPs from all the nodes. So once a node receives LSP from all the nodes, it will have the link state database, and that is what we call it as LSDB, which is nothing but it will have the link state packets of node A, link state packet of node B, link state packet of node C, link state packet of node D, and link state packet of node E. So all these LSPs putting together, that is what we call it as link state database. And the link state database will be used to create the shortest path. So with this idea in mind, we will see what happens next. So we will be creating the topology based on this link state database, but link state database or the topology is alone not enough to estimate the shortest path. We need some numbers. So this is how the knowledge will be there on each and every node. So as you can see, A will come to know that it is connected to B with the cost of 5, it is connected to C with the cost of 2, it is connected to D with the cost of 3. And similarly, each and every node has just created the topology, and this is what the knowledge that each and every node will have. Now it is not sufficient for us to create the shortest path tree, and also A does not know how to reach E, at least at this particular stage. Fine. So in this case, a shortest path tree is needed so that one node on the network will come to know about every node on the network and also the shortest route which it has to take to reach that particular destination. So here in this process of forming a shortest path tree, one node is called as the root node, and then all other remaining nodes will be visited from the root node. And the link state routing uses Dijkstra's algorithm to create the shortest path tree. Now we will see what exactly the Dijkstra's algorithm is and how the shortest path tree is being formed. So to explain the Dijkstra's algorithm, here is an informal representation of Dijkstra's algorithm and the various steps that is being undergone in the Dijkstra's algorithm. So rather than just reading this particular flowchart again, we will take an example and then we will try to see what happens in each and every step with this network. So now this is what an example network what we have, and let us try to apply Dijkstra's algorithm on this particular network, and we will see how the routing table or the shortest path tree is created at node A. So we will have 6 different steps and we will see what is happening at each and every step over here. So very first step, you need to set the root node and then it has to be moved to the tentative list. So before we even start the algorithm, we will be requiring 2 sets of list. So one is the permanent list and another one is the tentative list. So as per the flowchart, we need to first set the root node, and then I will set A as the root node over here. So now I will be trying to visit all other remaining nodes in the network from A, because A is my root node. I will like to travel all other remaining nodes from my root node A. So that is what the very first step is, and let's see how A is creating the shortest path. So first root node A is being identified, and then you need to enter that particular node in the tentative list. So fine, so let us put this entry on the tentative. Initially the permanent list will be empty, and then we will write A is connect. A can be reached with the cost of 0 and it is a directly connected node. We will put these informations on the tentative list. So set root node to A and move A to the tentative list. So that is what we have done in the first step. Now let us move again for the flowchart. So what is happening in the flowchart? We have to check whether the tentative list is empty or not. In case if the tentative list is empty, then we can stop the algorithm, but here the tentative list is not empty, so we need to further proceed with the flowchart. So here in this particular case, we need to check among the nodes in the tentative list, move the one with the shortest path to the permanent list. So we need to move the one with the shortest path to the permanent list. As of this particular step, we don't have any options available here. So what we will do is we will just move the available entry to the permanent list. So we will be moving A0 hyphen to the permanent list. So this step is being done, and then we will see what we have to do next. So add each unprocessed neighbor of the last moved node to the tentative list. So what I have to do is the last moved node to the permanent list is A. Now I need to add all the neighbors of A to the tentative list. Before moving it to the tentative list, we have to make sure that it is not already processed, or it should have the least cost. Now let us calculate, or let us just identify what are all the neighbors of A. So A can reach B with the cost of 5 and it is directly connected. So that is what the first entry of A, and the second entry or second neighbor of A is C, and we can reach C with the cost of 2 and it is a directly connected node. And then we can reach D with the cost of 3 and it is a directly connected node. So these three entries are the neighbors of A, we could say. Now none of these nodes are already processed because we have not at all visited B, C and then D. So that what we have to do is we need to add these entries to the tentative list. So I will add these entries in the tentative list. So B can be reached with the cost of 5 and it is a directly connected node, and C can be reached with the cost of 2 and it is a directly connected one, and D can be reached with the cost of 3 and it is a directly connected node. So the second step is being done, and then now I have to repeat this process until the tentative list is becoming empty. Now we have options here. Among these three options, the lowest cost available is C. So what I have to do is I need to move C to the permanent list. We already have A0 hyphen on the permanent list, and in addition to that I am moving C over here. Why I am moving C here? Because C has the lowest cost among the list available here. So now what I will do is I will just move C here. So I will write C2 hyphen on the permanent list. So once the permanent list is moved, I need to now add the neighbors of C to the tentative list. Now let us see what is the list that I'm getting if I move C over there. So the neighbors of C are, so this is for neighbors of A, and now I am writing for the neighbors of C. So A can, you have to always start reaching the particular node from A, right? So A can be reached. So the neighbors of C are B, E and then A. We pretty well know that, right? So neighbors of C are B, E and then A. Since A is already there on the permanent list, we need not consider moving this particular node again to the tentative list, which will create the duplicate routes. So it is enough to check B and then E. So via C, A can reach B with the cost of 6. So B can be reached with the cost of 6 via C. This is what the first entry that we will get. And then A can reach E with the cost of 6 via C. So these are all the two entries which I need to move in the tentative list. But here B, we have already an entry with the lowest cost. So we will be keeping this particular entry, not this one, because this particular entry is costing us more. So this entry need not be considered. We will go with the previous entry itself. Fine. So considering what are all the previous entries, so B5 and hyphen will be there, and then you have D3 hyphen, and now we have to add E6 of C, E6 via C to the tentative list. And now we have to repeat the procedure again. So now let us see what is happening next. Out of these available nodes, now D has the lowest cost over here, so I need to move D to the permanent list. Already we have A0 hyphen, and then we have C2 hyphen, and now we are moving D3 hyphen. Now let us put out the list of neighbors that is available at D. So D is connected only to A. Since A is already there on the permanent list, we need not again move this to the tentative list. So the list on the tentative list will not have any changes over here. So we will be left out with only two entries, that is B of 5 and E6 of C. So this is what the entries that we will have in the tentative list. Now we have to repeat the procedure. Out of these two entries, B has the lowest cost, so we need to move B to the permanent list. So we will have A0 hyphen, and then we have C2 hyphen, and we have D3 hyphen, and now we are moving B5 and hyphen. Now looking into the B's node, let us process the neighbors of B. The neighbors of B are A, C, and then E. So neighbors of B are A, C, and E. So I can reach A with the cost of 10 if I go via B, and I can reach C. Okay, let me just reveal the steps over here. So I can reach C with the cost of 9 if I go via B, and I can reach E with the cost of 8 if I go via B. So these are all the entries which I already got. These are all the entries which we will be getting by processing the neighbors of B. Because here in this particular entry, A is already processed, so we need not consider this. C is also already processed because it is in the permanent list. We need not process this. And now we have the tie for, means we have two entries for E. The previous entry says E can be reached with the cost of 6. But this entry says E can be reached with the cost of 8. Again, this is an highest cost, so we need not consider this. We will be going with the previous entry itself. So keeping this in mind, the entries will be E can be reached with the cost of 6 via C. So you should, at this particular point, you should understand why we are not updating the value of E, because when you reach E via B, then the cost will be higher. So if we are just in a process of identifying the shortest path. So that is why we are not taking the highest cost route. Now we will be repeating the procedure again. So the one and only entry what we have in the tentative list is E, and then we will be moving E to the permanent list. So A0 hyphen is what we already have, C2 hyphen is what we already have, D3 hyphen is what we already have, and B5 hyphen is what already have. Now we will be moving E to the permanent list. And after doing this, all the neighbors of E are already processed. The neighbors of E are B and then C. Both B and C are already processed, so that there is no other node which has to be added onto the tentative list. Now at this particular point, we could see that the tentative list is becoming empty, so that now at this particular point we can happily stop the algorithm since the tentative list is empty. And this is what we call it as the shortest path tree. As you can see, root node can now travel to all other remaining nodes in the network with the lowest path available. So the lowest path to reach B is with the cost of 5, and lowest cost to reach C is 2, lowest cost to reach E is 6, lowest cost to reach D is 3. And this is what we call it as the shortest path tree, which has been formulated by using Dijkstra's algorithm. So this is how the shortest path tree will be created, and with this the routing table can be easily framed. And this is how the routing table will be look like, and this represents the destination, and this represents the cost, and the third column represents the next router to which my table the packet has to be forwarded to reach the correct destination. So when you look at this particular routing table, and this routing table will be similar and it will be exact as the routing table what we got in the distance vector routing. So whatever be the algorithm that we are following, the end outcome is going to be the same. So this is how the link state routing will work. So these are all the various stages that is involved in creating a routing table, especially in link state routing. And then I'm going to stop the video here. I'm going to see you in the next video. Until then, it's bye from Jay and happy learning.